So the goal for us today, again, is to deconstruct these two problems. And in doing so, discover what are the important underlying properties of exponents that are going to let us analyze these problems. So first, let's put the focus just on the deconstruction part. How are we going to break these challenging problems down into simpler pieces? And then once we've gotten them into simpler pieces, I'm going to distribute those pieces among you and give you a chance to look at them individually. So let's come up with kind of an order of things that we can start to look at. The first thing I would do in these expressions is I'm going to follow the order of operations. The order of operations is going to prioritize what I look for. So according to the order of operations, what should be the first thing that I care about when I look at either of these two expressions? Parentheses. So let's first do what we can to simplify away parentheses. Simplify away all parentheses. Now, that means in both examples, really, we're going to look at the quantities inside the parentheses and ask, is there any way for me to simplify what's inside the parentheses? So in question number 1, what that would mean is I might first just take a look at this minus x to the third times z to the fourth and ask, can that be made any simpler than it already is? No, this is as simple as it's going to get. If we wanted to be really fancy, we could make it more complicated. We could write it as minus x times x times x times z times z times z times z. After all, that's what this notation means, right? But there's really no way for us to make this any simpler. We can't combine the x's with the z's. They're different variables, different variable factors, so we can't get the two of those together. So there's nothing I can do inside of those parentheses. How about the other set of parentheses here? 2x squared, y to the third z. Anything I can do to make that simpler? No. So at least at the moment, there's nothing we can do inside the parentheses on the first expression. What about in the second problem? Is there anything I can do here, anything that we think we might be able to do here, to the quantity inside the parentheses? When in doubt, you can always expand out the exponentials. M, 2, 3, 4, 5, 6, 7, n, n. Is there anything that we can do to reduce this fraction into lower terms? You're nodding your head. Why? Yeah. So remember, we can reduce a fraction into lower terms always by dividing by the same thing in the numerator and the denominator. What can I divide the numerator and the denominator by here in order to make this fraction simpler? What common factor do the numerator and denominator have?
4 m's.
Yeah, they've got a bunch of m's in common, right? I've got an m on top here that also matches with an m on the bottom. I've got a second, I've got a third, I've got a fourth. So there's 4 powers of m that are in common to the numerator and the denominator. In other words, if you like, m to the fourth. So what happens if I divide by all 4 of those powers of m? What's going to happen? How many powers of m are going to be left in the numerator after I divide 4 powers of m away? None. So I'll end up with only a 4 upstairs. How about downstairs? How many powers of m do I end up left with after dividing by m to the fourth? I end up with 3. So doing that, what happens to my n's, by the way? They stay there. What happens to this 3? Yeah, ditto. It just stays. After I do that division, I now have this fraction reduced into its lowest terms. One of the priorities for us today is to come up with a shortcut so that we can do that same process without having to write out all these factors every time. But writing them all out the first time that we do it will help us to understand where that property comes from, that we're going to actually be able to use. But that's going to give me that quantity inside the parentheses now in its lowest terms. So what that means that we can do to begin this simplification process is to simplify the quantity inside the parentheses according to what we just said. But then we still have, on the outside of it, parentheses with an exponent applied to the whole quantity. So now is a chance for us to, again, look at both places in these problems where there is an exponent that applies to the entire quantity. So here's an example, and then here's also an example. And ask, how can I get rid of these parentheses? Well, this is where one of the last things that we talked about is going to come in handy. Namely, the fact that exponents distribute over multiplication and division. When we were talking about the layer cake, this was one of the lessons from the layer cake. Exponents distribute over multiplication and over division. So what in particular does that mean for this exponent of 2 and the multiplication on the inside of these parentheses? What should I do? I should distribute. Distribute that exponent to all 3 of the factors. By the way, notice I sneakily recognized that there was a third factor of -1 out in the front here. Distribute that exponent across this multiplication. And what that gives me then is each of these 3 factors, -1, x to the power 3, z to the power 4, each one of those needs to be raised to its own second power. Second power, second power. So that is an illustration of this. Exponents distribute over that multiplication. Likewise down here, this exponent will distribute over this division, the fraction bar. So I'm going to do the same thing with that problem. So we're continuing to cut this problem down to size. We're going to apply that exponent to the 4 in the numerator, and then also to the entire quantity in the denominator. That exponent will apply here, and it'll apply there. But then again, I've got an exponent here with a multiplication inside the parentheses, and so what do I do there? Same thing. Distribute the 2 across the multiplication inside that set of parentheses. And that's going to give me then 3 squared times m to the 3rd power squared times n to the 2nd power squared. And we've gotten all this way with the only tool that we've needed was this distributive property, that exponents distribute over multiplication and division. I'm showing here a lot of steps that most students don't take the time to write down. But I encourage you, especially at this point in the course, to write these steps explicitly. Because it's when people try to bite off too many steps at once that they get too many different exponent properties confused in their brain and end up using the wrong type of arithmetic to simplify the exponents that we're going to try to simplify next. Our next step is to figure out how to go from here, because now we need to know how these exponents interact with the quantities inside, with the powers inside of the exponent. And then also, how can we bring all this information back? Even after we finish all of our distributive properties, we still need to reckon with how to raise a power to a power, as we have here. We have to reckon then probably with how do I take this power of x and this power of x and combine those powers of x together. And then also, we saw as an example in problem number 2, how do I do the reverse, which is to take a power divided by another power and simplify that. Right? So those are the 3 elements that we still need to have at our disposal, and those are going to be what we talk about next. Let's start with the quotient of powers property, the one that we have already seen kind of in action in this first example of what we did to simplify the quantity in number 2. So when we divided m to the 4th divided by m to the 7th, we ended up expanding out that power. So let me show you this group's work again here real quick. So we expanded out the power m to the fourth into 4 powers of m to the seventh into 7 factors of m. And then by dividing numerator and denominator by 4 powers of m, we ended up really just sort of canceling 4 of those away and getting 3 on the bottom. And what this group says is that that power 3 in the bottom is not surprising because it's the result from subtracting 4 from 7. Right? So when we canceled out those common factors of m, the number that remained is the difference between the larger and the smaller of those two numbers. Right? So we ended up in this problem subtracting exponents. So that might be the first clue as to how to combine powers together using exponent arithmetic. That quotients of powers lead to subtraction of exponents. And one of the issues that that raises is in this example, if we did 4 minus 7, we wouldn't actually get 3, we would get negative 3. So the last question I want to leave us with here is, what does it mean to raise something to the negative 3 power? It means exactly what we had just written up on the screen before, which is 3 powers of m in the denominator. One of the mental shorthands here is that wherever we started with more powers of m, we're going to end up with our remaining powers of m down there. We had more m's downstairs than we had upstairs. And so when all the cancellation happens, we still end up with our m's downstairs instead of upstairs. But that illustrates why a negative exponent is the same thing as an exponent in the denominator. So that's how we can justify the quotients of powers property. Let me make a small adjustment to what you have here. Roll the tape back here. I'll put my x to the 8th back in here. So when I multiply powers of the same base together, their exponents add. When I divide powers of the same base by one another, those exponents subtract. And then we kind of have the separate thing in our brain that says, well, if the exponent is negative, that means it belongs in the other part of the fraction. If it's in the numerator, it belongs in the denominator, and vice versa. And then when I take a power of a power, those exponents multiply. And that is a complete set of the properties that we need in order to finish simplifying the expressions that we have in this problem. So let's finish these two problems. First, let's worry about the constants. What's negative 1 in parentheses squared? That's just 1. Negative 1 times negative 1 gives me a positive 1. Now, following the order of operations, maybe I'll think about powers of powers first. X to the third raised to the second is going to give me how many x's? 6, because a power of a power leads to multiplying the exponents. Same thing with z to the fourth raised to the second. That was exactly the example that that group worked on. That gives us z to the 8th. And then over here I have multiplication by 2. I have x to the power 2, y to the power 3, and z. How many powers of z is this really, secretly? What exponent belongs here? Secret exponent of 1, yeah. It's a good idea to put it there to remind yourself of what's going to come next. But we won't do that yet. Let's go down to the example in problem number 2 to keep rolling with using this powers of powers strategy. So I've got here m to the third raised to the second. So how many m's do I have in that denominator? M to the power again, a power of a power leads to multiplying exponents, so yeah, 6. M to the power 6. And how about the n's? N squared raised to the second. N to the 2 times 2. And then out in the front here I have this coefficient 3 squared, which is going to give me 9. And actually, for problem number 2, now we're done. That strategy by itself was enough, since we did the quotients of powers things first. Actually, we did it kind of a little bit backwards. But now this one is completely simplified. So there's nothing more we can do to that one. And so the remainder of our work is going to happen in problem number 1. Where now, what's the property that we still have to use? Which one of these 3 do I still have to use to finish simplifying what I have in problem 1? how am I going to figure out, for example, how many powers of x there are in my final answer? Multiply the two powers of x together. I can do that, by the way, because multiplication is commutative, and therefore I can just move around these factors to get the powers of x next to each other, get the powers of z next to each other, get the numbers 1 and 2 next to each other. Right? So maybe I'll include that as a quick intermediate step. 1 times 2 times x to the 6th power times x to the 2nd power times y to the 3rd power times z to the 8th power times z to the 1st power. So I just get all the powers of a common variable right next door to one another, so that now I can focus on where the action actually is. Right here, where I'm multiplying 6 powers of x times 2 powers of x. Right here, where I'm multiplying 8 powers of z by 1 power of z. And then I can also simplify this product out here in the front, 1 times 2. And so now we have the roadmap to finishing this out. 1 times 2 is going to give me 2. X to the 6 times x to the 2 is going to give me how many x's? Right. Products of powers. I multiply the powers, and therefore I add the exponents. That gives me x to the 8th. My y to the power 3 doesn't have a dance partner, so it goes home alone, whatever, y to the 3rd. And then how many z's do we end up with? 9. Again, adding the exponents because we're multiplying the powers. And then we're done. Yeah. I made a copy error. Thank you. Yeah, there's one thing in problem number 2 that we forgot, which is namely this little exponent on the 4. What is 4 to the power 2? 16. By the way, another thing that people's brains misfire on very frequently when they're working with exponents is that they'll accidentally think of multiplication instead of thinking of exponentiation. And so often some people will write like 4 times 2. They'll make their exponent too large, and then in their brain they see it as multiplication instead, and they'll write it as 8. Those little mistakes, that's going to be the new sign error for a lot of people in this part of the course, is that their brain just sort of sees an exponent and interprets it as multiplication instead of as an exponentiation. So just be on your guard for that. 4 to the power 2 is 16, not 8. 3 to the power 2 is 9, not 6. 2 to the power 3 is 8, not 6. So just be extra careful. Exponent problems with just whole numbers like this one that seem simple on their face, just take an extra beat to think over it again in your head, because no matter how many times I say that, some of you will probably still make that silly error. So it's going to happen. Just try and keep your eyes open to make it happen less.